Earth is old, not metaphorically old, not the way a nation counts its centuries or a family traces its ancestry, but profoundly, cosmically ancient. 4.5 billion years of change, upheaval, silence, and rebirth. Its mountains have risen and crumbled. Oceans have vanished and returned. Continents have torn apart and crashed together like drifting rafts on a molten sea. What we call the world is not a single place, but a sequence of worlds layered over each other, each one as real as ours, and now gone. In this long, slow procession of time, life has come and gone in forms too strange to fully grasp. Trilobites with compound eyes, fern forests stretching beneath carbon-thick skies, dinosaurs whose bones are now part of cathedral walls, mammals the size of buses. And among all that, only in the final blink of this planetary lifetime did something we might call intelligence emerge. Fire, language, structure, memory. Only now, in these last 300,000 years, have beings appeared who wondered where they came from, and only in the last century have they looked beyond the sky. This raises a quiet, troubling question. Why did it take so long? If Earth has been hospitable to life for more than 3 billion years, why did no intelligence appear sooner? Why is the rise of civilization not a gradual crescendo, but a sudden spike, sharp, recent, isolated? We assume, because of our own presence, that intelligence is inevitable, that given enough time, something like us will emerge. But what if intelligence is not a destination, but a flicker? Not a final chapter, but a brief line, written then erased. And what if we are not the first line? Our history is short, our ruins younger than a desert's breath, and the silence beneath our feet may not be empty. It may be memory, folded, buried, waiting. We imagine that civilization leaves footprints, skyscrapers, satellites, roadways stretching like veins across a continent. We think if something like us had come before, surely we would know. There would be artifacts, blueprints, bones shaped by tools. But this confidence overlooks a simple, relentless truth. Earth does not preserve, it erases. Everything we build, steel, plastic, concrete, is made for our lifetime, not for geologic time. Exposed metal corrodes and flakes. Plastic shatters, crumbles, becomes invisible. Concrete fractures and falls back into sand. Even the bones of our cities are no match for wind, for rain, for heat. A jungle reclaims a highway in years. A coastline swallows a port in decades. In 1,000 years, even our most advanced monuments become ghostly outlines beneath the soil. In 10 million, they are gone. We live in a narrow frame of memory, believing that what we leave will last. But the earth does not care for memory. It folds, it churns, it buries, and it burns. Mountains rise and vanish. Rivers cut new paths. Continents shatter and collide. Entire oceans are consumed by the planet's crust, taking with them anything built upon their floor. So ask, if a civilization had risen 50 million years ago, what would remain? Would we see their roads, their machines, their signatures carved in stone? Or would we find only faint chemical anomalies, scattered isotopes, a strange pattern in the fossil record? Things we might misread or miss entirely. Perhaps we are not looking for ruins. Perhaps we should be looking for echoes. Stone remembers, but only for a while. The surface of our planet is not a static canvas. It is a restless, moving, living crust, broken into vast plates that drift, grind, and sink into the molten mantle below. This slow-motion dance, called plate tectonics, is both creator and destroyer. It raises mountains, builds continents, and then swallows them whole. The ocean floor, for example, is never older than 200 million years. In a planet that has existed for 4.5 billion, this means entire eras, entire worlds have been erased without a trace. Even on land, permanence is an illusion. Wind scours stone into dust. Rain and ice pry apart cliffs grain by grain. Rivers carve valleys, glaciers grind mountains to rubble. In a blink of geological time, cities become ruins, ruins become rubble, rubble becomes sand. Layer by layer, these sediments are buried, pressed, heated, and reborn as new rock. The past, quite literally, recycled into the present. When we look for traces of what came before, we are sifting through fragments of a planet that has been rebuilt countless times. Only a tiny fraction of Earth's original surface remains untouched, hidden in rare cratons, ancient rock shields that survive the planet's relentless reworking. The rest is a palimpsest, a story written, erased, and written again. If all of Earth's history were compressed into a single year, life would appear in early March, complex organisms in late November. Dinosaurs would rule until December 26th. Humans, all of human history, from the first carved tools to the satellites in orbit, would occupy the final seconds before midnight on December 31st. And when the clock strikes 12, the record may be gone again. In the search for life beyond Earth, there is a paradox. The universe is vast, ancient, and filled with billions of stars like our Sun, many with planets in the so-called habitable zone. If life is common and intelligence is a natural step in its evolution, then the galaxy should be teeming with civilizations. Yet, we see nothing. No signals, no structures, no unmistakable signs that we are not alone. This silence has led some scientists to propose a sobering idea: the Great Filter. It is not a wall we can see, but an invisible threshold, a stage in the progression from lifeless matter to a spacefaring civilization that almost no one survives. Somewhere along the chain, from the first molecules to multicellular life, from intelligence to technology, from technology to the stars, there is a point at which most civilizations end. The filter could be at the very beginning, making the spark of life vanishingly rare. It could be at the step from simple to complex organisms, meaning few worlds ever grow more than algae and microbes. It could be at the leap to intelligence, or at the mastery of tools and machines. And it could be waiting beyond where we stand now, a point where technological societies inevitably destroy themselves by war, by environmental collapse, by something we have not yet imagined. If the Great Filter lies behind us, humanity may be one of the rare survivors, the first in a vast desert of empty worlds. But if it lies ahead, then the silence of the stars is not just a mystery. It is a warning. If others came before us, why is the earth silent? If there were civilizations in deep time, builders, thinkers, storytellers, why can we not find even a whisper of them in the ground beneath our feet? One possibility is that they faced their own great filter and did not pass through. Civilizations rise quickly in geological terms. They flourish for thousands, maybe tens of thousands of years, a heartbeat in the planet's lifetime. And then they vanish. Their cities crumble. Their roads are swallowed by forest or sea. Their works are ground into dust, washed into rivers, drawn down into the mantle by the slow churn of tectonic plates. Time does not just bury the past, it recycles it. It is possible that Earth has seen this happen not once, but many times. A cycle of emergence, mastery, and collapse. Each iteration leaves traces, but not the kind we expect. Not standing monuments or clear records. Instead, perhaps a thin layer of unusual sediment, a shift in isotopes, a sudden change in the fossil record. Things that could be dismissed as natural unless we knew exactly what to look for. And maybe that is the problem. We are looking for familiar shapes, for tools, for bones, for structures. But what if the truest evidence of an ancient civilization is chemical, geological, almost invisible to the untrained eye? What if the absence of ruins is not proof of absence, but proof of inertia? If others have walked this planet before us, why have we never found them? Not just in the fossil record, not just in the artifacts of archaeology, but in any unmistakable signal that says, "We were here." The question is deceptively simple, yet it cuts deep. Are we certain we know what to look for? Are we sure that evidence of a civilization must look like ours, with metals, concrete, and glass? Or could it be something entirely different, shaped by a technology we would not even recognize? Our search has been narrow, focused on the obvious and the tangible. But history, especially the history written in stone, is rarely obvious. The traces of the past may be subtle, a pattern in isotopic ratios, a sudden anomaly in carbon layers, microscopic debris in ancient ice, or a deposit of metals that should not be there. These are not the sorts of things we stumble upon by chance. They must be sought deliberately, with the right questions in mind. This is the purpose of our journey, to step outside the familiar timeline of human history and search the deeper record, the billion-year memory etched into the rocks, the ice, and the seabed, to examine every whisper of an anomaly, every unexplained structure, every chemical oddity that refuses to fit neatly into the story we tell ourselves about Earth's past. Somewhere in that vast, silent archive may be the evidence that we are not the first. And if we find it, we may also find the answer to a far greater question: whether we will be the last. 2 billion years ago, in what is now the equatorial forests of Gabon, West Africa, a strange fire burned. It was not the orange flame of wood or grass, but the invisible chain reaction of atoms splitting, a nuclear fire sustained and controlled for hundreds of thousands of years. Today, we call it the Oklo phenomenon, and its discovery in the 1970s sent a quiet shock through the scientific community. Miners had been extracting uranium from the Oklo deposit when they noticed something unusual. The uranium ore was depleted in the isotope U-235. This was not a minor variation. It matched the exact kind of depletion seen in the fuel rods of modern nuclear reactors after use. In other words, this uranium had already undergone fission long before humans even existed. The explanation, at least on the surface, was that Oklo had been the site of a natural nuclear reactor, a geological arrangement of uranium ore, groundwater, and other factors that allowed a self-sustaining chain reaction to occur without any human intervention. The physics worked. The chemistry matched. And yet, the implications remained unsettling. Because if this was a natural reactor, it was one of the most improbable coincidences in Earth's history. And if it wasn't entirely natural, then someone or something had been here before us, with a mastery of nuclear science we only rediscovered in the last century. It is an idea that most scientists approach with caution, but it is a question that refuses to fade. In the deep past, did the planet itself stumble upon the secrets of the atom, or did it inherit them? For a nuclear chain reaction to occur, nature must arrange a remarkably precise set of conditions. At Oklo, all of them seem to have fallen into place. The uranium ore there, 2 billion years ago, contained about 3% uranium, 235, the lighter fissile isotope capable of sustaining a chain reaction. That number is critical. Too little U-235 and the reaction fizzles out. Too much and the reaction runs uncontrolled. 3% is the Goldilocks zone, just right for steady fission, the same concentration we enrich fuel to in modern reactors. But uranium alone is not enough. Neutrons released by fission move too fast to efficiently trigger more fissions unless they are slowed down. At Oklo, the moderator was natural, groundwater seeping through the porous rock. This water acted exactly as the graphite or heavy water in modern designs, slowing neutrons to the right speed, allowing the chain reaction to continue. Even more surprising was the reactor's apparent ability to regulate itself. As the reaction heated the water, it boiled away, removing the moderator and causing the fission rate to drop. When the rock cooled, water flowed back in, slowing neutrons again and restarting the reaction. This cycle of on and off could have repeated for hundreds of thousands of years, preventing the kind of runaway scenario that would have destroyed the reactor zone. By every measurable parameter, isotope ratios, neutron moderation, thermal cycling, Oklo functioned exactly like a purpose-built nuclear reactor. The only difference is that it operated nearly 2 billion years before anyone we recognize as human ever walked the Earth. When scientists first proposed the natural reactor explanation, it seemed elegant enough, a rare but plausible accident of geology. But the more they examined Oklo, the less accidental it appeared. For such a reactor to start and sustain itself, the list of requirements is exacting. The uranium ore must be concentrated to roughly 3% U-235. The groundwater must flow in a stable cycle, seeping through the rock at the right rate to moderate the neutrons without flooding the reaction zone. The surrounding minerals must be free of neutron-absorbing impurities such as boron or cadmium, which would shut down the chain reaction instantly. Each of these conditions is improbable on its own. Together, their occurrence should be vanishingly rare, a 1 in millions geological coincidence. And yet, Oklo did not host just one such reactor zone. It had 17 separate sites, all within the same region, each meeting the delicate balance needed for sustained fission. This repetition pushes the limits of chance. Why here and nowhere else? Uranium deposits exist across the world, some even older than Oklo's. Yet no other site, ancient or modern, shows the same clear evidence of a long-lived, self-regulating reactor. Was there something unique about Gabon's geology? A subtle, unrepeatable arrangement of minerals and water flow? Or was there something else? And there is another puzzle: the timing. 2 billion years ago, the proportion of U-235 in natural uranium was just high enough to make fission possible. That ratio declines over time due to radioactive decay. If the Oklo reactors had formed even a few 100 million years later, they would not have worked at all. The window for such a natural reactor to exist was narrow, and Oklo sits almost perfectly in the center of it. Coincidence or precision? When researchers analyzed the uranium ore from Oklo in detail, they found patterns that felt familiar. The isotopic signatures, The relative amounts of U-235 and its daughter products matched those produced in modern nuclear reactors after extended operation. The waste products were there too, isotopes of neptunium and plutonium, which do not occur in significant amounts in nature, but which can be formed inside a reactor through neutron capture. These isotopes have short half-lives compared to the age of the site, so they should have long since decayed into other elements. And yet, in Oklo, their decay products were found exactly where the reaction had taken place, with no sign that they had been washed away or dispersed into the surrounding environment. In other words, the nuclear waste had stayed put for 2 billion years. That in itself is remarkable. In a modern reactor, we go to great lengths to store spent fuel in ways that prevent contamination of air, water, or soil. At Oklo, it seems nature or someone did the same. The fission products are locked within the mineral matrix, trapped in stable compounds that prevented their spread. Even the distribution of xenon isotopes, noble gases that normally escape quickly, is frozen in the crystal structure of the rock, as though sealed there by rapid cooling or deliberate containment. To the mainstream explanation, this is simply an outcome of unique geological conditions. To others, it looks suspiciously like engineering, a system that not only produced nuclear energy, but also kept its byproducts in place, avoiding contamination. Whether by design or by an improbable stroke of natural fortune, the result is the same. A nuclear site as clean and stable as any built by human hands. Most geologists and nuclear physicists accept Oklo as a natural phenomenon, a lucky alignment of conditions that happen to occur in one place at one moment in the planet's history. 2 billion years ago, Earth's atmosphere held far less oxygen, which allowed uranium deposits to remain rich and unoxidized for long periods. The region's hydrology may have been unusually stable, with slow-moving groundwater passing through the ore body at just the right rate to moderate the reaction. The uranium ore itself might have been sheltered from erosion and leaching, preserving its concentration until the critical moment. Oklo was an accident of deep time, a chemical and geological chain of events that, while rare, required no guiding hand. And yet, even proponents of this explanation acknowledge that the timing had to be perfect. The U-235 ratio in natural uranium has been steadily declining since Earth's formation. 2 billion years ago, it was barely high enough to allow fission, and a few 100 million years earlier or later, the reaction could never have started. Then there is the symmetry of the site itself. 17 separate reactor zones, each displaying the same self-regulating pattern, each preserving its waste products in a way that has prevented contamination for billions of years. Even with all the known geological factors, the uniformity across these zones remains difficult to explain. So while the natural reactor theory may be the most conservative answer, it still demands a sequence of coincidences so precise in timing, location, and chemistry that it feels less like an accident and more like a puzzle waiting to be solved. There is another possibility, one that sits far outside the comfort zone of conventional geology, but refuses to vanish from the discussion. What if the Oklo reactors were not the product of blind chance at all, but the deliberate work of an intelligent hand? In this view, the matching isotope patterns across all 17 zones would not be the outcome of improbable coincidence, but the signature of engineering. The self-regulating on-off cycle, driven by the movement of water, might have been intentionally tuned to prevent runaway reactions. The fact that radioactive waste remains locked in place after 2 billion years could point to a purposeful design for containment, a system that kept harmful byproducts from spreading, much like the spent fuel storage systems we build today. If the Oklo reactors were truly the work of an ancient intelligence, then our understanding of history would be shattered. It would mean that the story of technological civilization on Earth did not begin with us, or even with our species. It began 2 billion years ago, in an age we cannot imagine, when the continents were shaped differently, the air was unbreathable to us, and life itself was still in its earliest complex forms. Such a discovery would force us to redefine what it means to be first. Humanity would be revealed not as the singular pinnacle of evolution, but as one chapter in a much longer book, a book whose earlier pages have been erased by the grinding machinery of time. It would mean that intelligence can arise, master the forces of nature, and then vanish so completely that only the subtlest geological traces remain. And if that is true, then the silence that follows becomes more than a mystery. It becomes a warning. The absence of our predecessors' voices could be the echo of their collapse, the moment when they met their own great filter. Whatever ended them left no survivors, no memory, no record, just the faint residue of their greatest achievement locked inside the rocks of Gabon. If they fell, so can we. And perhaps that is the real gift of Oklo, not as proof of who came before, but as a quiet reminder that survival is never guaranteed, even for those who hold the power of the atom. In 2018, a climate scientist and a planetary physicist posed a question that sounded more like science fiction than serious research. If an industrial civilization had existed on Earth millions of years before humans, would we be able to tell? The scientist was Gavin Schmidt, known for his work on climate modeling and director of NASA's Goddard Institute for Space Studies. His collaborator was Adam Frank, an astrophysicist who studies planetary atmospheres and the long-term habitability of worlds. They published their proposal in the International Journal of Astrobiology and gave it a name that raised eyebrows: the Silurian hypothesis. The term came from the Silurians of Doctor Who, a fictional race of reptilian beings who developed advanced technology before humans appeared, only to retreat underground. Schmidt and Frank were quick to clarify the name was a playful nod to pop culture, but the content of their work was entirely serious. Their idea was not to prove dinosaurs had built cities, but to explore a thought experiment. What kinds of geological traces would an ancient industrial civilization leave behind? And would those traces still be visible tens or hundreds of millions of years later? It was a question that challenged both paleontology and our own assumptions about how we would recognize intelligence, on Earth or anywhere else. Imagine for a moment that during the late Cretaceous or the Jurassic, a species had risen to dominate the planet, not merely in size or numbers, but in thought. They mined, they built, they burned fuel, they reshaped landscapes. Now move the clock forward 100 million years. What would be left for us to find? Schmidt and Frank's question cut straight to the limits of our science. Would any trace of such a civilization still exist in the geological record? Or would time erase them completely? Stone buildings would crumble in a matter of millennia. Metal would corrode and vanish even faster in most climates. Plastics might persist longer, but over millions of years, even they would break down into microscopic residues, indistinguishable from naturally occurring polymers. And that raises a deeper challenge. Even if something survived, would we recognize it as artificial? A thin layer of unusual chemicals and sediment could be the byproduct of an industrial age, or the result of volcanic eruptions, asteroid impacts, or shifts in ocean chemistry. The further back in time we look, the more these signals blur into one another until cause and effect become guesswork. If an industrial civilization had flourished among the dinosaurs, our only clues might be subtle. Shifts in isotope ratios, strange patterns in mineral deposits, a sudden change in climate chemistry. Nothing like the clear ruins or artifacts we imagine. The Earth's memory is long, but not perfect. And the deeper we dig into it, the more we must ask whether the silence we hear is real or just the result of looking in the wrong way. Among the dinosaurs, a few species stand out not for their size or strength, but for their brains. The Troodon, for example, possessed one of the largest brain-to-body ratios of any known dinosaur, rivaling that of modern birds and approaching the lower range for mammals. Its eyes faced forward, granting it stereoscopic vision, an advantage for judging distance and depth. Its hands were flexible, capable of grasping, and its predatory lifestyle demanded problem-solving skills far beyond simple instinct. Velociraptors and other dromaeosaurs showed evidence of coordinated hunting, suggesting not just intelligence, but social structures. Some species cared for their young, guarding nests and feeding hatchlings. Others migrated in groups, responding to seasonal changes, behaviors that in mammals often accompany complex communication and planning. If evolution had been granted another 20 or 30 million years before the asteroid struck, what might these traits have become? A slightly larger brain here, a more dexterous hand there, incremental changes adding up over geological time. Intelligence is not unique to mammals. It has evolved independently in birds, cephalopods, and certain reptiles. There is no reason to think dinosaurs were exempt from this potential. In this light, the notion of a tool-using dinosaur is not fantasy, but an extrapolation, a reminder that intelligence is an adaptive trait like any other. Given time, it can emerge in forms we might never expect, and perhaps in ages long past, it already did. The fossil record is a narrow window into the past, and it is far from complete. Of all the creatures that have ever lived, only a tiny fraction left behind bones or shells durable enough to fossilize, and an even smaller fraction of those have been found. Soft-bodied organisms, or those living in environments that do not favor preservation, vanish almost entirely from history. If this is true for life itself, it is even more so for the traces of technology. Cities, tools, and engineered structures fare poorly against the slow violence of geology. Stone crumbles, metal corrodes, concrete disintegrates. Within tens of thousands of years, nature reclaims even the most imposing constructions. Within millions, they dissolve into the sedimentary layers, indistinguishable from the rock around them. The Earth's crust is in constant motion, and over hundreds of millions of years, entire continents shift, mountains rise and fall, and the surface is recycled. The challenge is even greater if an ancient civilization lived along coastlines, as we do today. Oceanic crust is replaced on a cycle of roughly 200 million years, meaning that any record of coastal or seafloor settlements from the age of dinosaurs would be completely erased. The seabed where they once stood would have been subducted into the mantle and reborn as new crust, taking every trace of that history with it. In such a dynamic planet, the absence of evidence may not be evidence of absence. It may simply be the result of a world that is always in the process of erasing its own past. If a civilization had thrived during the age of dinosaurs, the most enduring traces would likely not be their buildings or tools, but subtle chemical signatures locked in the geological record. Layers of sediment might show abrupt changes in composition. Spikes in heavy metals like lead, chromium, or rare earth elements that do not fit the surrounding context. Shifts in carbon isotope ratios, such as an unusual depletion of carbon-13, could signal the large-scale burning of fossil fuels, altering the balance of the atmosphere in ways distinct from natural processes. Other clues might be changes in soil chemistry, residues of synthetic compounds, or anomalies in mineral deposits that align with industrial extraction. These indicators would be indirect, requiring careful interpretation and comparison against known geological events like volcanic eruptions or asteroid impacts. For example, if a civilization had powered itself by burning coal or oil, its legacy would not be a preserved city, but a thin, planet-wide layer of altered carbon chemistry embedded in ancient sediments. Such a fingerprint could persist for millions of years, even if every physical artifact was gone. And yet, all of these possible markers face the same problem. They can be explained by purely natural phenomena. A volcanic event could mimic the same isotopic shifts. An asteroid impact could spread heavy metals across the globe. Without a clear and distinguishing pattern, something we could not attribute to nature alone. The case for an ancient technological species remains a tantalizing but unproven speculation. Gavin Schmidt and Adam Frank have always been clear about one crucial point. They have no evidence whatsoever for the existence of a dinosaur civilization. The Silurian hypothesis is not an earth-shattering archaeological discovery, but rather a thought experiment. A question designed to probe the limits of our understanding of planetary history. Their goal is to force us to reconsider how we read and interpret the geological record. If every trace of an industrial civilization could vanish within just a few million years, do we actually have the methods and tools to detect it? And more importantly, if we can overlook intelligence right here on our own planet, a world we have studied for generations, how confident can we really be that we would recognize it on a distant world? This question expands the scope of the search for extraterrestrial life, not just looking for crumbling cities or abandoned spacecraft, but reading the subtle clues in rock, ice, and atmosphere. Because sometimes silence is not an answer. It is the result of not yet knowing how to ask the right question. If the dinosaurs had ever developed a technological civilization, where are they now? The fossil record tells us that most of them vanished at the end of the Cretaceous, likely due to a catastrophic asteroid impact. But if an intelligent species existed among them, their fate might not have been so simple. They could have perished in the same global disaster, their achievements erased in a geological instant. Or perhaps they reached a level of technology capable of destroying themselves through warfare, environmental collapse, or other self-inflicted means. The great filter may have claimed them long before they could leave a lasting mark. And then there is the more speculative possibility. What if they did not vanish entirely? Could remnants have adapted, gone underground, or retreated to environments inaccessible to us? Could they have evolved into something no longer recognizable as their former selves? Not flesh and bone, but something else entirely? These questions may never have definitive answers, but they remind us that the silence in the fossil record does not necessarily mean nothing happened. It may simply mean that whatever happened was swallowed by time, and that our own story might one day meet the same fate. Most of what we know about the ancient world comes from fossils, and fossils, by their nature, are the record of life, not the record of industry. They capture the bones of creatures long gone, the shells of marine life, the impressions of leaves in ancient mud. They do not capture the works of cities, the frameworks of machines, or the artifacts of a technological age. So if there had once been a civilization of steel and glass, of concrete towers and intricate devices, why do we not see them in the geological record? Perhaps the answer lies not in their absence from history, but in the limitations of preservation itself. A fossil can preserve the curve of a rib for hundreds of millions of years, but the girders of a bridge, the circuitry of a computer, or the span of a spacecraft would vanish long before they could ever be transformed into stone. The silence we find in the rocks may not be a verdict. It may simply be the boundary of what those rocks can hold. Fossilization is not a common fate. It is an extraordinary one. For it to occur, the remains of an organism must be buried quickly, sealed away from oxygen, and surrounded by mineral-rich waters that slowly replace organic matter with stone. These conditions are rare, fragile, and specific. They favor the preservation of life's hard parts, bone, shell, wood. And even then, only a fraction survive long enough to enter the fossil record. Metals, plastics, and the engineered composites of human industry do not follow the same path. They corrode, crumble, or dissolve long before they can mineralize. The gears of a machine will rust into nothing. An airplane's frame will be eaten by chemical reactions. A titanium alloy, strong against modern weathering, will eventually fracture and vanish under geological timescales. The fossil record, for all its depth, is tuned to biology. It has no memory for cars, circuitry, or the skyscrapers that might have once touched the clouds. Metal feels eternal in our hands, cold, solid, unyielding. Yet in the measure of deep time, it is among the most fragile of materials. Copper will tarnish and pit within decades. Iron and steel, though they can shape empires, surrender to oxygen in only centuries, crumbling into reddish dust. Aluminum resists rust, but falls prey to other chemical attacks, dissolving into oxides and salts. Even the stainless steels and aerospace alloys we prize for their resilience slowly degrade, undone by electrochemical processes and the quiet work of microbes that feast on metal. Give the Earth 100,000 years, and it will strip every bolt, every rail, every tower back to elemental grains. After 1,000,000 years, nothing remains for the fossil record to catch. The physical signatures of engines, bridges, and power grids dissolve into the geologic background. Their sharp edges lost, their stories erased, before they could ever be written in stone. Plastics, the signature material of our age, seem impervious when new. Smooth, waterproof, resistant to rot. In sealed environments, They may endure for centuries, but under open skies, they face an array of relentless enemies. Ultraviolet light from the sun breaks the bonds between their polymer chains, turning solid objects brittle until they fragment into dust. Microbes, once thought powerless against synthetic polymers, have begun evolving enzymes to digest them. Heat accelerates every reaction, twisting and snapping the molecular structure until only chemical residue remains. Advanced composites, such as the carbon fiber or Kevlar, promise strength far beyond steel, yet without controlled preservation, they too unravel into powders and flakes. Even concrete, our most enduring building material, is far from immortal. Moisture infiltrates, freezing and thawing until the structure fractures. Acid rain leaches minerals, leaving it weak and crumbly. 10,000 years without maintenance would reduce our tallest towers to scattered mounds of aggregate. In the theater of deep time, all human materials are temporary props, destined to bow and vanish before the next act begins. Life itself is a patient, tireless dismantler. Fungal hyphae thread their way into micro cracks, prying them wider with each season's growth. Bacteria, invisible to the eye, feed on metal surfaces, releasing acids that corrode steel and copper from within. Tree roots probe deep into foundations, splitting stone and concrete with slow, irresistible force. The very soil, rich with organic acids, seeps into buried structures, turning once solid alloys into flakes of oxide or crystals of soluble salts. Rain, laced with industrial pollution, falls as acid, leaching the strength from both metal and stone. Sunlight does its own quiet work, breaking chemical bonds in plastics and composites, fading colors, weakening molecular integrity until a structure crumbles at a touch. Water, persistent and adaptable, infiltrates every gap, swelling porous stone, rusting rebar, shattering walls as ice expands within. Even in stillness, the planet moves against permanence. Given centuries, the combined actions of life, air, and water leave no monument untouched. And given millions of years, they leave nothing at all. The archaeological record is not a complete library of the past. It is a handful of torn pages, scattered by time, recovered only where chance has preserved them. What survives is dictated not by importance, but by durability and circumstance. A stone tool, chipped from flint, may endure for hundreds of thousands of years, while a spacecraft's alloy hull could vanish without a trace in less than 1% of that span. The irony is stark. The more advanced the material, the less likely it is to fossilize into history. Our picture of the past, then, is not drawn from a balanced archive, but from the stubborn fragments that happen to resist decay. And so, absence in the ground is not proof of absence in reality. It is only a reminder of how much the Earth has already erased. Archaeology, by its very nature, is tuned to a certain kind of past. The past of farmers, potters, and stonecutters. We search for shaped flint, worked bone, fired clay, and carved stone because those are what endure. This focus makes sense for the Neolithic world. But what if the civilization we seek was not agricultural at all? What if it was industrial, synthetic, or even post-organic? What if its tools were woven from materials designed to vanish back into the biosphere without a trace? In that case, the most telling evidence would not be a shard or a skeleton, but a subtle chemical fingerprint in the soil, a shift in isotopes, or an unexplained layer in ancient sediments. We may be standing on the remnants of such a world right now. But without the right questions and the right instruments, we would never know. We peer into deep time through the fractured lens of the fossil record, seeing only the shards that survived 1 billion trials of erosion, pressure, and decay. It is a mirror, cracked and clouded, showing more gaps than shapes. If an ancient civilization once walked this planet, nature would have treated its creations no differently than the shells of ammonites or the bones of giant reptiles, breaking them down, dissolving them grain by grain, until nothing recognizable remained. In such a world, the question is no longer, why haven't we found them? But rather, what else might be here that we have not yet learned to see? The silence of the earth may not be emptiness at all, only a language we have not yet learned to read. When a city collapses, its streets crack, its buildings decay, and vegetation slowly reclaims the ruins. In a few centuries, only faint outlines remain. In a few million years, even those are gone, buried, eroded, and folded into the Earth's crust. If an industrial civilization had once thrived hundreds of millions of years ago, we would not expect to find their streets, machines, or towering monuments today. But perhaps something else would survive, not their shapes, but their invisible fingerprints. Subtle chemical changes, ecological disruptions, scars in the atmosphere and oceans. These can endure far longer than steel or concrete. When we peer into ancient strata, sometimes we find such scars, anomalies in the Earth's chemical record that whisper of a past we have never known. One of the most sensitive indicators of planetary upheaval lies in the ratio of carbon isotopes preserved in ancient rocks. Scientists call it delta 1,3C, a measure of how much carbon-13 is present compared to carbon-12. Under normal conditions, this ratio changes slowly over geological time. But in certain layers of Earth's history, we find abrupt, dramatic drops in delta 13C, a phenomenon known as carbon-13 depletion. These plunges are not random. They often coincide with mass extinction events, moments when biodiversity collapsed and ecosystems unraveled. One possible cause? A sudden surge of CO2 into the atmosphere, overwhelming the carbon cycle. This can happen through massive volcanic eruptions or through the large-scale burning of organic carbon, such as coal and oil. The latter is especially intriguing. When fossil fuels burn, they release carbon that is naturally poor in carbon-13, diluting the global ratio. In our own time, industrial emissions are creating just such a signal, one that will be permanently etched into the geological record. If an ancient industrial civilization had once relied on fossil fuels, its activity could have left behind a nearly identical isotopic fingerprint, still visible today in the stone pages of Earth's history. Alongside carbon anomalies, the geological record sometimes reveals another kind of fingerprint: unusual concentrations of heavy metals. Layers of ancient sediment have been found containing elevated levels of lead, mercury, arsenic, cadmium, and other toxic elements. In the natural world, such metals occur in trace amounts, dispersed and harmless. But in much higher concentrations, they become markers of something extraordinary, either catastrophic natural events or deliberate extraction and processing. In our own era, heavy metals saturate soils and waterways primarily through mining, metallurgy, and industrial waste. The same pattern appears in the stratigraphic record at certain points in deep time, prompting the question, what caused it back then? Massive volcanic eruptions can indeed flood the environment with mercury and other elements. Yet volcanic signatures usually come with other telltale signs, ash deposits, basalt floods, that don't always align neatly with these anomalies. Could these ancient spikes instead be the legacy of a forgotten technological age? If some long-lost civilization once smelted ores, forged tools, or powered machines, the chemical scars of their industry could remain embedded in the rocks even after every artifact had turned to dust. The history of life on Earth is punctuated by mass extinction events, but two in particular stand out, not only for their devastation, but for the strange fingerprints they left behind. The end Permian extinction, approximately 252 million years ago, was the most catastrophic biological collapse in our planet's history. An estimated 90 to 95% of all species vanished, both on land and in the oceans. The geologic layers from this time reveal dramatic delta-13 sea shifts, indicating a sudden and massive disruption of the carbon cycle. Heavy metal concentrations spike in parallel, suggesting either unprecedented volcanic activity or some other vast environmental disturbance. Evidence also points to severe ocean acidification and widespread anoxia, oxygen-depleted seas covering much of the planet. The end Cretaceous extinction, approximately 66 million years ago, is better known. The event that ended the age of dinosaurs. High levels of iridium in the boundary layer have long been attributed to a colossal asteroid impact. Yet, the story is more complex. Alongside the iridium are signs of rapid climate instability, disrupted carbon isotopes, and ecological collapse far more intricate than a single instantaneous blow. In both cases, the environmental shifts happened on unnervingly short timescales in geologic terms, too fast, too synchronized across the globe to be easily explained by slow-moving natural processes. The combination of carbon anomalies, heavy metal spikes, and ecological meltdown is eerily reminiscent of patterns scientists see emerging today during the Anthropocene, where human industry is the driving force. Could these great die-offs have been triggered, or at least accelerated, by the actions of an industrial civilization that has since been erased from history? Imagine a geologist from a distant future brushing away the dust of 10 million years, revealing a thin, strange layer in the rock. It would be unlike anything in the strata above or below it, a compressed signature of a world that suddenly changed. Within that layer, they would find a sharp drop in carbon-13, the kind of isotopic shift that only happens when unimaginable amounts of carbon dioxide flood the atmosphere. They would detect specks of lead and mercury evenly scattered across the globe, from the ocean floor to the poles, elements that don't appear together in nature except when dragged there by industry. Fossilized remains would tell another story. Species vanishing in a geological blink, ecosystems collapsing, life itself reshaping under invisible pressure. That layer is us. It's the Anthropocene, an epoch defined not by the slow grind of tectonic plates or the chaos of a meteor strike, but by the brief and furious activity of one species. In the rock record, it'll read as a sudden convulsion. Altered isotopes, chemical intrusions, and a mass extinction all stacked together in one razor-thin slice of time. And if that future geologist had never heard of humanity, how would they interpret it? Perhaps the way we now puzzle over the end Permian or end Cretaceous events, seeing only the scars, wondering what force could have left them. The uncomfortable possibility is that somewhere deep in Earth's history, Another layer just like ours might already exist. The last breath of a civilization that came and went before we were even imagined. If an ancient civilization once walked this earth, we may never hold their tools in our hands or walk through the ruins of their cities. Stone and steel crumble, concrete collapses, and even the hardest alloys dissolve into dust under the patient chemistry of the planet. The relics we imagine, gleaming towers, intricate machines, would not survive the relentless grind of millions of years. But Earth is a meticulous archivist of consequences. While it erases the form, it preserves the fingerprint. The chemistry of the air, the subtle shifts in isotope ratios, the unnatural patterns of metals in stone, all are whispers left behind when life alters the planet on an industrial scale. Perhaps that is all we will ever find, not the civilization itself, but the echo of its passing. A thin line in the rock where the atmosphere changed. A shimmer of metal where it doesn't belong. A sudden, irreversible reshaping of ecosystems. Footprints not carved in stone, but etched in the molecular architecture of the biosphere. And if those traces already exist in the deep past, then we are not the first to leave them. We are simply the latest, adding our own layer to the geological archive, one that another intelligence someday might study as they wonder who we were and why we vanished. When we think of fossils, we imagine bones turned to stone, the coiled shell of an ammonite, or the delicate imprint of a fern leaf on shale. But some fossils are invisible to the naked eye. They are written not in shape or texture, but in the very balance of atoms locked deep within the rock. In these atomic signatures, there are no skeletons to admire, no broken statues to study. Only the silent ratios of isotopes, the tiny differences in uranium, xenon, or neodymium that whisper of energies once unleashed. These anomalies are more than geological curiosities. They are fingerprints, unchanged for billions of years, of processes so specific that today they occur only inside the heart of a nuclear reactor. And if such a reactor had existed long before humans walked the earth, who or what built it? To seek the answer, we begin our story in the heart of Africa, in Gabon, where the ground hides a 2-billion-year-old puzzle, the Oklo phenomenon, a place where the bedrock itself remembers a time when atoms were split and refuses to forget. At its core, nuclear fission is brutally simple. Take an atom of uranium-235, strike it with a wandering neutron, and watch it split. In an instant, the atom becomes something else. 2 smaller nuclei, a burst of energy, and a spray of new neutrons racing off to repeat the process. But the split is never neat. It leaves behind a trail of exotic byproducts, xenon, neodymium, ruthenium, atoms with weights and properties that nature does not casually produce in bulk. They are the industrial waste of the atomic world. In a natural deposit of uranium, the ratio between its 2 main isotopes, U-235 and U-238, is constant. Today, it's about 0.720% U-235. But after a sustained fission reaction, that balance changes. The stock of U-235 drops, replaced by those telltale fission products, many of which have no plausible origin outside a nuclear chain reaction. These products are not fleeting. Xenon can be trapped within minerals like time capsules. Neodymium isotopes will remain stable for millions, even billions of years. Long after steel has rusted to dust and concrete has crumbled to gravel, these atomic fingerprints endure, etched into the rock itself. To a trained scientist, that isotopic pattern is as distinctive as a human fingerprint. It tells a clear story. Here, in this very place, atoms were split, deliberately or otherwise, and the rock has remembered every detail. In the summer of 1972, a shipment of uranium ore from a mine in Oklo, Gabon, arrived in France for processing. Routine tests were performed, nothing out of the ordinary, until one detail set off alarm bells. The concentration of uranium-235 was wrong. Instead of the standard 0.720% found in every other natural deposit on Earth, Oklo's ore measured about 0.717%. That might sound like a trivial difference, but in the precise world of nuclear chemistry, it was enormous, far too large to be explained by measurement error. It was as if someone had already used up part of the U-235. Curiosity turned into alarm when deeper analysis revealed a second anomaly. The ore was laced with unmistakable fission products: xenon-136, neodymium-143, cesium-135. Exactly the isotopes created in the core of a modern nuclear reactor. They weren't just present. They were present in the same ratios engineers see in human-built reactors today. The conclusion was as startling as it was unavoidable. Roughly 1.7 to 2 billion years ago, right there in the heart of West Africa, a sustained chain reaction had run for hundreds of thousands of years. Water had seeped through the uranium-bearing rock, acting as a natural moderator, keeping the process stable and self-regulating. Today, Oklo stands alone in the geological record, a place where the Earth itself, under a set of improbable conditions, built and operated a nuclear reactor. At least, that's the official explanation. Whether it was purely nature's handiwork or something else entirely remains one of science's most intriguing open questions. Nuclear fission is not something that just happens under everyday conditions. For a chain reaction to ignite and sustain itself, 3 very strict requirements must be met. First, the proportion of uranium-235 must be high enough to support a chain reaction. 2 billion years ago, natural U-235 abundance was about 3%, just on the edge of viability. Second, there must be a moderator, something to slow down fast neutrons so they can split more nuclei. In Oklo's case, that role was played by groundwater seeping through the deposit, a perfect natural coolant and moderator. Finally, the reaction must be prevented from running away into a meltdown. In human-made reactors, this is done with careful engineering, control rods, cooling systems, negative feedback loops. Yet Oklo's reactor zones operated with an almost eerie balance, cycling on and off in a self-regulating rhythm. The water heated up, boiled away, the reaction paused, the water returned, and the chain reaction resumed. It was the sort of automated control even modern engineers would be proud of. And here's the deeper puzzle. If this could happen naturally, why only here? Uranium deposits exist all over the planet, yet no other site, past or present, shows the same signs. Was Oklo a freak accident of geology? Or the carefully chosen location of a project long forgotten? When scientists examined Oklo's isotope ratios, they found something uncannily familiar. The distribution of fission products, xenon-136, neodymium-143, cesium-135, was almost indistinguishable from the waste output of a contemporary nuclear power plant. It wasn't just a vague similarity. It was a match down to the subtle details of how certain isotopes accumulate and decay. Even more intriguing was the evidence of neutron poisoning. the buildup of elements like samarium-149 that absorb neutrons and slow the reaction. In modern reactors, this is a major operational challenge that requires careful monitoring and management. At Oklo, this process seemed to happen naturally, then somehow resolve itself, allowing the reaction to restart. The reactor zones cycled through on-off phases in a way that mimicked modern load-following operations, a feat so precise that even today's engineers must model it meticulously to avoid catastrophic failures. At some point, the coincidences start to feel excessive. Perfect uranium concentration, perfect water flow, perfect containment of radioactive byproducts, all in a configuration that runs for hundreds of thousands of years without a meltdown. So we must ask, was nature simply having a lucky day in Gabon 2 billion years ago? Or did someone, something, recognize the site's potential and shape it into a power source? If so, what else might they have left behind, now erased by time? If a civilization 2 billion years ago possessed the ability to manipulate nuclear fission, we would not expect to find their cities or machinery still standing. Time would have erased the concrete, the metal, the very foundations. The oceans would have turned their structures to sand. The continents themselves would have shifted, swallowing any trace. And yet, something would survive. The atomic signature. Unlike stone or steel, isotopic anomalies are immune to erosion and decay. The altered U-235/U-238 ratio, the peculiar abundance of xenon-136 or neodymium-143, these are fingerprints that can linger for geological ages, written not on the surface of the world, but in the arrangement of its atoms. This is all we truly have from Oklo. No reactor halls, no cooling towers, no control rods. Just a pattern in the isotopes, quietly declaring, a reactor was here. The danger is that modern science, constrained by its own assumptions, may be mistaking an engineered artifact for a quirk of nature. We label it a natural nuclear reactor because that is the neatest explanation within our worldview. But what if our worldview is incomplete? What if we are reading the last surviving message from a vanished technological epoch and filing it away as a geological curiosity? Skeptics of the ancient reactor hypothesis often invoke Occam's razor. The simplest explanation is usually the correct one. In the case of Oklo, they say that explanation is a natural nuclear reactor, an improbable but not impossible geological coincidence. But what if the simplest explanation is not the one that fits most neatly within our present worldview, but the one that best matches the evidence itself? What if the data, those stubborn isotope ratios, those unmistakable fission products, are telling a story far stranger than we are willing to entertain? Perhaps our hesitation comes from a reluctance to rewrite the deep history of technology. We are comfortable imagining civilization as a recent phenomenon, a brief spark in the darkness. To admit otherwise would mean accepting that others may have risen long before us, wielding powers we are only now rediscovering and vanishing without a trace but for the atomic whispers locked in stone. So we are left with a question that will not easily go away. Was Oklo a natural wonder or the last surviving fragment of a forgotten atomic age? Until we dare to look beyond our own assumptions, that answer may remain buried, not in rock, but in our own caution. Over the past 500 million years, Earth's story has been punctuated by violence, not the kind waged by armies, but by forces so sweeping they reset the stage of life itself. At least 5 times, The planet has suffered mass extinctions so severe that between half and nearly all living species vanished. Each event rewrote the evolutionary script, erasing entire branches of life's tree in a geological instant. Oceans emptied, forests withered, entire predator-prey networks collapsed into silence. For most of history, we've explained these calamities as purely natural disasters: asteroids, supervolcanoes, climate swings. But the speed, intensity, and odd chemical signatures of some of these events leave room for a more unsettling question. Were they always natural? Or could some have been the fingerprints of technology, wielded by civilizations we have long since forgotten? If you could stand on some eternal mountaintop and watch the last 500 million years unfold beneath you, the story of life would not feel like a gentle evolution. It would look more like a city struck by fire after fire, rebuilt each time on the ruins of the last. Whole worlds would bloom in dazzling variety, only to be scythed down almost overnight, replaced by stranger, sparser survivors. The first great cut came in the Ordovician, around 444 million years ago. The seas were kingdoms of trilobites, corals, and shelled creatures until an abrupt climate shift, likely a brief but brutal ice age, froze the oceans and drained the shallow seas. In what must have felt like a geological blink, 85% of marine species were gone. Some 70 million years later, the Devonian suffered its own drawn-out collapse. It didn't come as a single blow, but in waves. Reefs withering, fish lineages vanishing, entire coastal ecosystems crumbling over millions of years. By the end, 3/4 of marine life had disappeared, leaving a quieter, emptier ocean. Then came the Permian, 252 million years ago, the closest life has ever come to total erasure. Volcanic fury, poison seas, a sky choked with ash. Whatever the exact cause, it was enough to annihilate 96% of marine species and 70% of land vertebrates. Forests withered, deserts spread, and the biosphere seemed to gasp for breath for millions of years afterward. Scientists call it the Great Dying, and the name is no exaggeration. The Triassic, 201 million years ago, ended in another upheaval. Volcanic eruptions tearing apart the supercontinent Pangaea, releasing enough carbon to warp the climate. Amphibians and early reptiles fell in droves. But for the dinosaurs, it was an open door to dominance, one they would stride through for the next 135 million years. Finally, 66 million years ago, the Cretaceous curtain fell. The asteroid that carved the Chicxulub crater in what is now Mexico brought darkness, firestorms, and a collapse of the food chain. The dinosaurs, save for the ancestors of today's birds, vanished. Alongside them went the great marine reptiles, the spiral-shelled ammonites, and countless plants and plankton species. 5 times, life was brought low. 5 times, Earth remade itself in the shadow of catastrophe. And yet, the question that lingers is unsettling. Were these cataclysms purely the work of nature? Or did something or someone help pull the trigger? Most natural changes in Earth's history are slow dances. Continents drift like sleepwalkers. Climates shift over hundreds of thousands of years. Species rise and fade in a long evolutionary tide. But some extinctions don't move at that pace. They arrive like a hammer blow. The end of the Permian is one such moment. In the geological record, it plays out not as a slow fade, but as a sharp drop, a cliff edge. One layer of rock holds a vibrant, crowded fossil world, sponges, corals, fish, forests, and the very next is almost empty. The change may have taken only a few thousand years, perhaps even less. For the planet's 4.5 billion year history, that's not just fast, it's instantaneous. The end of the Cretaceous tells a similar story. In many places, the fossils vanish between layers no thicker than a human hand. Above that thin line, filled with iridium-rich dust, the dinosaurs are gone, the great marine reptiles gone, the lush plant ecosystems reduced to a skeletal remnant. Whatever struck the planet did not give ecosystems time to stagger, adapt, and recover. It erased them in one sweep. In each of these events, the fossil record shows the same haunting pattern. A narrow band of rock marking a sudden global collapse in biodiversity. It is the geological equivalent of finding an entire city abandoned overnight, food still on the tables. Was this the hand of nature, wielding volcanoes or asteroids? Or could such sudden synchronized devastation also be the fingerprint of something else? A disaster not born in the crust or sky, but in the mind of a species that had learned to reshape the planet. When scientists confront the scars of mass extinction, they reach for the most powerful forces in nature. For the great dying at the end of the Permian, the prevailing suspect is fire from below. The Siberian traps, an eruption so vast it poured oceans of lava across the land for hundreds of thousands of years. It's a compelling image, an Earth that choked on its own molten breath. But even this vision falters under the clock. The speed of death recorded in the rocks, the near-instant collapse of ecosystems, seems too abrupt for volcanic cataclysms alone, which usually unravel life over tens of thousands, not mere thousands, of years. For the dinosaurs' twilight, the smoking gun appears to be a rock from the sky. The Chicxulub impactor slamming into the Yucatan with the force of billions of nuclear bombs. The iridium-rich dust it left behind is as close to a signature as science gets. And yet, the fossil record whispers a more complex story. Some species were already in decline before the asteroid struck. Climate shifts and disrupted food chains were underway, signs that something else had started the killing before the final blow fell. Then there is the quiet, persistent explanation of natural climate change, shifts in ocean currents, gradual cooling or warming, fluctuations in atmospheric gases. These forces are real and have shaped life countless times before. But in these particular extinction events, they fail a crucial test. They move too slowly, and they rarely strike with such synchronized precision across land, sea, and sky. Each official story explains much, but not everything. And in the gaps, those moments where the Earth's heartbeat stops almost at once, lies space for a darker possibility, one that does not begin in magma chambers or asteroid belts, but in intelligence and technology turned against the world itself. But what if the hand that tipped the balance wasn't a volcano or an asteroid? What if it was a hand like ours? Imagine a civilization so advanced that its wars were fought not with swords or spears, but with forces capable of dimming the sun. Planet-wide conflict could have unleashed weapons that cloaked the skies in dust, choking photosynthesis and collapsing the food web in months. Or perhaps the end came not with a bang, but through relentless appetite, a culture drawing too heavily on its planet's stored carbon, burning ancient fuels, reshaping its atmosphere, could have driven the climate into chaos, melting ice, acidifying oceans, and suffocating marine life. There is also the specter of scientific ambition gone awry. Experiments with energy beyond their full understanding, chemical reactions on a global scale, or even nuclear processes might have spiraled out of control, altering air and water in ways no ecosystem could survive. In the geological record, the aftermath of such acts would look eerily familiar. Rapid extinctions, chemical anomalies, climate shocks. The cause might be mistaken for nature's fury, but the speed, precision, and global reach could just as easily be the fingerprints of technology turned against its own makers. If we dig deep into the rocks laid down during the great die-offs, we find more than just fossils turned to stone. We find whispers of chemistry gone wrong. In some layers, the concentration of carbon dioxide and methane spikes sharply, a surge that would feel familiar to anyone watching the emissions charts of our own time. It's the kind of atmospheric shift you might expect from the burning of vast reserves of fossil fuel, flooding the air with greenhouse gases. Elsewhere, geologists have measured unusual buildups of rare metals, elements like platinum group minerals, or traces of heavy metals such as mercury and cadmium. In nature, these appear only in scattered small amounts. In industry, they are the lifeblood of electronics, catalysts, and advanced machines. Their sudden abundance in ancient sediments begs the question, was this the byproduct of a purely geological process, or the waste of an industry now lost to time? And then there are the isotopic oddities, subtle distortions in the ratios of certain elements, the kind of patterns that today emerge from nuclear fission or fusion. These are changes you don't get from volcanism alone. They are precise, measurable, and stubbornly resistant to weathering. An atomic echo that could last billions of years. Individually, these clues can be explained away. Together, they sketch the outline of something far more deliberate, an ancient handprint, blurred but not entirely erased, in the deep archive of the Earth. If a civilization had once walked this planet long before us, they might have climbed to heights we can barely imagine, mastering energy, reshaping landscapes, perhaps even reaching for the stars. And yet, in the end, they could have been undone not by slow decay, but by a single catastrophic misstep. From this perspective, the great mass extinctions take on a darker meaning. They may not have been the causes of a civilization's disappearance, but the aftermath, the silent consequence of choices gone wrong. A war too vast, an energy experiment too ambitious, or a planet's climate tipped past the point of return. If that is true, then the Great Filter is not some distant cosmic hazard still waiting for us out there. It is already here, built into the fragile balance of life on Earth. These extinction events are not random acts of nature. They are the checkpoints where almost every attempt at lasting intelligence has failed. And if history really has seen this cycle before, then we may already be approaching the same invisible threshold, the point beyond which survival is no longer guaranteed. Look up at the night sky and you're staring into an ocean of worlds. Astronomers tell us there are at least 100 billion galaxies, each holding hundreds of billions of stars, and far more planets than there are grains of sand on all the beaches of Earth combined. The math is overwhelming. Somewhere out there, under alien suns, life should be blooming. Civilizations should be building, communicating, exploring. And yet, nothing. No radio whispers drifting through the cosmic background. No glints of colossal engineering blotting out starlight. No visitors, no probes. No faint echoes of industry across the void. Just a stillness so complete it feels almost unnatural. This is the puzzle that physicist Enrico Fermi crystallized one summer afternoon in 1950 over lunch with colleagues. He put it simply, almost casually: where is everybody? That question has haunted scientists ever since, and it is the doorway into one of the most unsettling ideas in astrobiology: the Great Filter. This is the puzzle that physicist Enrico Fermi crystallized one summer afternoon in 1950 over lunch with colleagues. He put it simply, almost casually: where is everybody? That question has haunted scientists ever since, and it is the doorway into one of the most unsettling ideas in astrobiology: the Great Filter. The story goes that in the summer of 1950, physicist Enrico Fermi was having lunch with fellow scientists at Los Alamos. The conversation had wandered from nuclear tests to space travel, to the sheer number of stars and planets that must exist in the Milky Way. Fermi, known for his razor-sharp logic, suddenly paused, set down his fork, and asked a question that sliced through the room's chatter. If there are so many advanced civilizations out there, where is everybody? It was more than idle curiosity. By the numbers, the galaxy should be teeming with intelligent life. The Drake equation, a simple but provocative formula for estimating the number of detectable civilizations, suggests that even with conservative assumptions, there could be hundreds or thousands of technologically capable societies in our galactic neighborhood. And yet, when we look for them, the cosmos answers only with silence. No radio transmissions bleeding across the interstellar dark. No autonomous probes silently surveying our solar system. No unmistakable engineering projects. No Dyson spheres. No planetary scale beacons interrupting the regular heartbeat of the stars. It is as though the universe is hosting a grand party and we arrive to find the room empty, or perhaps emptied. Imagine the story of life as a long, treacherous road stretching from the barren surface of a newborn planet to the glittering expanse of interstellar civilization. Along the way are gates, not mere doorways, but towering barriers that almost no traveler survives. The Great Filter, as scientists call it, is one of these gates. No one knows exactly where it lies. It might be far behind us, hidden in the improbable moment when lifeless chemistry stirred into biology, when the first fragile cell split in two. It could lurk in the almost miraculous leap from single cells to multicellular life, a step so rare it took Earth billions of years. Or perhaps the real test came later, when certain animals began thinking in ways that could shape tools, language, and eventually technology. But there's one gate more dangerous than all the others, surviving our own inventions. A civilization that learns to harness vast power, whether nuclear fire, planetary engineering, or machines smarter than the makers, must also learn restraint, fail, and the gate slams shut forever. The Great Filter could be any of these moments. It could be all of them. The unsettling truth is that we can't tell if humanity has already passed it, or if it still looms ahead, waiting patiently in the shadows of our future. If the story of life is a gauntlet of impossible trials, then humanity has already survived some of the most brutal rounds. We've crossed the chasm from single cells to multicellular complexity, leapt from instinct to reason, and forged the strange magic of language, that invisible thread binding minds across time. We've even built machines that can amplify our reach, letting us touch the moon and probe the edges of the solar system. Yet, for all that progress, we are still standing on the narrow ledge before the most perilous climb of all, becoming a civilization that endures, not just for a few centuries, not just until the next war or disaster, but for tens of thousands, perhaps millions of years. A civilization that lives across planets, insulated from the death of any single world, immune to its own self-destructive impulses. And so the question gnaws at us: is the great filter already behind us in those ancient and unlikely steps that brought us here? If so, perhaps we are alone because no one else ever made it this far. Or is the filter still ahead? A silent, inevitable wall that no species, however brilliant, has yet found a way to pass. There's a strangely comforting possibility hidden inside the great silence. Maybe the reason no one has knocked on our cosmic door is that no one else has ever built a door. Perhaps life that can think, dream, and shape the world around it is so astronomically rare that humanity is the first, or at least the first in our galaxy, to emerge. If that's true, then every empty sky we gaze upon isn't a sign of failure, but of unprecedented success. We have already passed the bottlenecks that crushed countless other worlds before they could give rise to minds like ours. The void is not a graveyard of civilizations, but untouched wilderness waiting for its first explorers. It's a vision laced with hope, but also with weight. If we are the first, then the responsibility is ours alone, to keep the light burning, to carry life beyond Earth, and to ensure that the story of thinking beings in the universe is not a short one. The stars may be silent now, but perhaps they are waiting for us to speak first. The darker interpretation of the great filter flips the comforting story on its head. In this version, the silence of the stars isn't because no one else has risen. It's because everyone who has fallen. Civilizations may have bloomed across the galaxy only to be erased before they could stretch beyond their homeworlds. If this is true, we are simply the latest in a long, doomed line. The threats aren't distant science fiction. They are seeds we already carry. Nuclear arsenals capable of scouring continents, artificial intelligences that could slip beyond our control, ecosystems teetering toward collapse. And perhaps the real danger is something we can't yet imagine. A catastrophe that no species has ever anticipated in time. In that light, the cosmic silence becomes ominous. It's not the absence of life, but the echo of its destruction. If the filter lies ahead, we may be racing toward it without even knowing it's there. Another brief flare in the universe, soon to wink out. How could we ever know if the great filter is behind us or still looming ahead? Paradoxically, the answer might come not from the stars themselves, but from the smallest and simplest forms of life. If we discover microbial life on Europa's icy oceans, or detect chemical whispers of biology in the atmosphere of a distant exoplanet, it might not be the celebration we imagine. Life, it would suggest, sprouts easily. And if it sprouts easily yet, the galaxy remains silent. The filter probably lies ahead. That would mean intelligence and survival past the technological threshold are far rarer than we'd like to believe. On the other hand, if we scan 1,000 worlds and find only barren rock and sterile seas, perhaps we are the rarest thing in the cosmos, a species that has already hurdled many invisible gates no other life has managed to cross. That would make us both an accident and a miracle. Either way, the universe's quiet is not passive. It feels like a test, a vast, unblinking challenge to our assumptions, waiting to see whether we'll decipher its meaning before it's too late. We stand at a crossroads in cosmic history, balanced between two possibilities. We might be pioneers, the first voice to rise in a galaxy that has known only silence. Or we might be just another in a long line of civilizations, each burning bright for a moment before vanishing into the dark. The silence around us is not an empty void. It is a mirror reflecting the path ahead. It shows no images of our past, only faint outlines of our potential and our peril. In the cold, unlit stretches between the stars, the question has shifted. It is no longer, where is everybody? It is this: will we endure long enough to be remembered, or will we too dissolve into the silence? Today, Mars is a frozen desert, a barren landscape of dust, rock, and thin air. The winds hiss over lifeless plains, and its pale skies give little warmth. Yet scattered across its surface are scars that tell a different story. Winding riverbeds, sprawling deltas, the ghostly outlines of ancient shorelines. Billions of years ago, this was not the Mars we know. It had liquid water, a thick atmosphere, and a climate that could cradle life. Something changed, catastrophically and forever. The rovers and orbiters have brought back whispers from Mars's deep past. Clay minerals that only form in long-standing water, spherical hematite blueberries shaped in aqueous environments, and layered sediment that once lay at the bottom of lakes. The chemistry of its rocks speaks of rivers that ran for millennia, of rainfall that fed a planetary water cycle, evaporation, condensation, precipitation, echoing the rhythms of our own Earth. For a time, Mars might have been a habitable twin, painted in blues and greens instead of rust-red dust. Methane, fleeting and fragile in Mars's thin atmosphere, has been detected again and again, rising and falling with the seasons. On Earth, such methane is often the breath of life, produced by microbes, though it can also be born from certain geological processes. Ancient Martian rocks have also yielded thiophanies, chlorobenzenes, and carbon chains. Organic molecules that, while not proof of life, are the raw materials from which biology is built. Some minerals on Mars match those found on Earth in places teeming with microbial ecosystems. If life emerged early on Earth, it could just as easily have bloomed on Mars, which shared similar conditions in that era. One possibility is that Mars was the cradle, and fragments of its life, carried by meteorites, seeded Earth. Another is bolder, that Mars once harbored its own civilization, which rose and fell long before humans walked the Earth. Or perhaps it was never home to a native people at all, but instead a sanctuary or even a colony for an ancient terrestrial civilization fleeing a dying Earth. Mars's death might have been slow, a gradual unraveling after its magnetic field faded. Without that shield, the solar wind stripped away its atmosphere, bleeding oceans into space. But it could also have been sudden. An asteroid strike, a volcanic upheaval, or a polar shift. And then there is the possibility no one dares to name, that Mars destroyed itself. Perhaps a technological mistake, a runaway climate spiral, or a planetary-scale resource collapse turned a living world into a frozen tomb. Like Venus, Mars could be a cautionary tale written in planetary stone. Today, our machines crawl over Mars's dusty plains, drilling into rocks, sniffing the air for traces of ancient life. Officially, we are looking for microbes, the simplest spark of biology. But perhaps we are unknowingly excavating a forgotten chapter of our own story. Maybe nothing remains. No ruins, no monuments, no cities, only a scattering of isotopes and subtle shifts in the chemistry of the land. Yet stones can speak, if we learn to hear them. And perhaps Mars has been whispering to us all along. Venus is the very image of a hostile world. Surface temperatures hot enough to melt lead, crushing air pressure 92 times greater than Earth's, and clouds that rain sulfuric acid. It is the last place one would imagine life. And yet, the evidence suggests that this scorched wasteland may once have been a temperate, ocean-bearing paradise. Data from orbiters and climate models paint a picture of a younger Venus with shallow seas, gentle temperatures, and a sky that could have sheltered life. If that world existed, it didn't just fade away. It was destroyed. The question is, how? The dominant theory is a runaway greenhouse effect. It began when Venus started losing its water, stripped away by heat and relentless solar radiation. Without water vapor to help regulate temperature, carbon dioxide was left free to build in the atmosphere. The hotter it became, the more CO2 was released from dried seabeds and carbonate rocks. This feedback loop spiraled upward, each degree of warming unleashing more gas, until the entire planet was locked in a permanent thermal overdrive. Venus became a sealed pressure cooker, a place where the air itself could crush and burn. If Venus once had an environment stable enough for life, then it's not unthinkable that it may have also harbored an intelligent civilization. And if so, what if they helped accelerate their own destruction? Imagine a society that harnessed energy on a vast scale, releasing greenhouse gases into an already warming climate. They may not have needed war or weapons to end their world. Only a slow but relentless disruption of its natural balance. If this happened, all traces would be gone. No fossils, no ruins, no artifacts, just a silent, lifeless sphere wrapped in clouds of poison. Venus's surface is young, geologically speaking, just 500 million years old. Something catastrophic reshaped it, erasing its older history. The cause could have been volcanic resurfacing, tectonic convulsions, or something more exotic. Its atmosphere contains strange chemical compounds that are difficult to explain through known geological processes. In the upper clouds, fast-moving jet streams swirl with layered structures eerily similar to Earth's ozone layer. Whether these are remnants of natural processes or the ghost of industrial chemistry, no one can yet say. Venus stands as a mirror to our own future, a vivid example of what happens when a planet's climate tips into chaos. Understanding why it changed is not just a planetary science question. It is a survival question. The idea of a lost Venusian civilization is not about chasing UFO legends. It's about asking whether we are truly different or whether we are just at an earlier chapter of the same story. Civilization or not, Venus is the monument to ecological collapse on a planetary scale. If life ever thrived there, we are the only ones left to bear witness and to learn. One catastrophic misstep in managing a biosphere may have happened before, just across the void, and if we are not careful, it could happen again. But this time, the name of the planet will be Earth. 2.5 billion years ago, the air was poison, at least to the creatures who called Earth home. The oceans swarmed with life, but it was a life that had never tasted oxygen, a life that thrived in its absence. These ancient microbes breathed in a world of methane, carbon dioxide, and nitrogen, and to them, oxygen was not the stuff of survival, but a corrosive toxin, a molecular assassin. The disaster began not with a cataclysmic impact or a volcanic eruption, but with something far quieter: the evolution of a new way to capture sunlight. Cyanobacteria, tiny blue-green architects of the planet's future, had discovered photosynthesis. They split water molecules, used the hydrogen to build sugars, and released oxygen as waste. At first, this waste gas vanished into the oceans, reacting with dissolved iron to form vast layers of rust that settled on the seabed. The banded iron formations geologists would one day find. But eventually, the oceans could hold no more. The iron was saturated, and the oxygen began to spill into the air. Slowly at first, then in a relentless tide, it accumulated in the sky. For the dominant life forms of the time, it was as if the entire atmosphere had turned to cyanide. Their proteins warped, their metabolisms collapsed. Species that had ruled the Earth for billions of years died out, some within the span of geological moments. And yet, not all vanished. A few found ways to endure. Some retreated into the deep mud, hiding in oxygen-free pockets beneath the seabed. Others evolved defenses, molecular shields that could neutralize the new toxin, intricate membranes that kept the hostile gas out. If survival is a kind of technology, then these were their machines, not of steel and fire, but of enzymes and lipids, crafted by the logic of evolution and, perhaps, by something more deliberate. It's tempting to imagine that there was, in that ancient microbial world, a kind of civilization, not with cities or language, but with cooperation, with shared survival strategies passed down in genes rather than books. To such a society, the Great Oxidation would have been an apocalypse. Their atmosphere turned alien, their oceans poisoned from above. They may have faced the same choice we fear today: adapt or die. We cannot know their stories. No monuments remain, no artifacts lie buried in the rocks. Only subtle chemical ghosts in ancient sediments, shifts in carbon and nitrogen isotopes that whisper of a time when the planet's chemistry changed faster than life could follow. In the end, oxygen reshaped the Earth, paving the way for complex life and much later, for us. But it came at a cost. To the life that came before, our breath would be as deadly as the air would be to us. And that is the paradox the Great Oxidation leaves us with. Every great leap forward for one kind of life may be the death sentence for another. History, we are told, follows a straight line. First came the stone tools, then bronze, then iron. A steady march toward the present, without detours into the impossible. But every so often, something turns up in the ground that doesn't fit the story at all. Archaeologists have a name for such anomalies: out-of-place artifacts, or OOPARTS. These are objects that, according to the geological layers they're found in, simply should not exist. A nail sealed in ancient limestone, a machined sphere entombed in rock older than multicellular life. Most are quietly set aside, dismissed as hoaxes or misinterpretations. And yet, some linger in the record, stubbornly defying easy explanation. In the red hills of South Africa, miners have pulled from the pyrophyllite rock strange metallic spheres, perfectly shaped, some with etched grooves running their circumference. The stone that cradled them is 2.8 billion years old, long before the first fish swam the seas. In France, 19th century quarrymen splitting chalk blocks found hollow metal tubes embedded in the strata. The chalk itself dated to the twilight of the dinosaurs. And scattered across continents are fossilized imprints that look eerily like sandal treads, wheel tracks, or carved patterns preserved in rock laid down tens of millions of years before the first humans. skeptics have good reasons to raise an eyebrow. Some discoveries can be explained by much younger rock intruding into older layers, or minerals crystallizing into patterns that mimic human handiwork. Others are outright forgeries made to fool collectors or chase newspaper headlines. But not all have been so easily dismissed. A handful of samples still sit in museum drawers or research labs, awaiting further study. Anomalies that have survived decades of scrutiny without a final verdict. One Russian report tells of a gear-like structure found embedded in Carboniferous coal over 300 million years old, its teeth evenly spaced as if machined. In another case, a ring-like object made of an alloy unknown to any known culture was recovered from deep within prehistoric sediment. No clear origin story fits without breaking the accepted timeline of technology. If these objects are genuine, the possibilities fracture into strange directions. They might be the last remnants of a forgotten civilization, erased so thoroughly that only scraps of its handiwork remain. Or they could be nature's own imitations, the geological equivalent of a face in the clouds, shaped by chance but carrying no intent. And in the most speculative corner, one could imagine something far stranger, temporal accidents or coincidences so improbable they feel like intrusions from another age entirely. Mainstream science often avoids the subject, and not without reason. Careers are built on reproducible data, not on singular anomalies no one can replicate. Funding agencies are wary of research that flirts with the sensational, and yet ignoring an anomaly is not the same as explaining it. The truth is that human history, as we define it, is only a thin film over the 4.5 billion year surface of the Earth, 0.004% of its age. We have barely scratched the topsoil of time. Whether parts are mistakes, misreadings, or the footprints of something that walked before us, they remind us of one essential truth. Our knowledge of the past is not a fortress, but a tent in a storm. One day, perhaps, a single undeniable artifact will emerge from the rock. Something so precise, so out of place, that the old story will crumble. And when it does, we will have to write the beginning of history all over again. Every night, the moon hangs above us, a pale sentinel keeping silent watch over the turning Earth. We have looked at it for as long as there have been eyes to see, but we rarely think of it as anything more than a companion, a barren, lifeless rock. Yet in truth, the moon may be something far more extraordinary, a vault, a library without words, holding the lost history of our world. Unlike Earth, the moon has no atmosphere to stir its dust, no wind to erode its scars, no rain to wash away the past every impact. Every grain of dust that has landed there over billions of years remains. Its surface is not a shifting canvas like Earth's, but a palimpsest where nothing is ever erased. The moon does not forget. When a great meteorite strikes Earth, the violence is so intense that rock, soil, and sometimes even seawater are hurled beyond the pull of our gravity. Some of that debris finds its way to the moon, a mere 3 days' journey through the void. There, with no air to burn it and no weather to wear it down, it settles gently into the regolith and waits. In those fragments could be the DNA of ancient microbes, molecules from oceans long vanished, or even chemical traces of forests, deserts, and volcanic landscapes that no longer exist. The moon's vacuum is a perfect deep freeze. No oxygen, no liquid water, no decay. If Earth's early life or lost environments still have a physical trace anywhere, The moon may be keeping it safe. Scientists have begun to take this idea seriously. Missions like NASA's planned Moonrise, as well as programs from ESA and China, are targeting the far side and ancient basins to look for these terrestrial refugees. Some of the most coveted samples would be from the Hadean and Archean eons, the mysterious first 2 billion years of Earth's history, now erased from our own crust by tectonics and time. And if, in the most speculative but tantalizing possibility, there was once an advanced civilization on Earth, now completely obliterated, then the moon may hold its only surviving artifacts: a fragment of metal alloy that does not rust, a shard of glass shaped by an intelligent hand, even a piece of machinery flung skyward by an asteroid strike. On Earth, such things would be ground to dust. On the moon, they could survive for eons, untouched. But the moon's archive does not end with Earth. It also carries the history of the solar system itself, a record of ancient asteroid bombardments, the changing rhythms of the sun, and the violent epoch known as the Late Heavy Bombardment. Every crater is a timestamp. Every buried layer of dust is a page in a book written across time and space. When we finally return, not just to visit, but to dig, to sift, to read, we may discover that the moon has been keeping a chronicle of our world since before our world could speak. While Earth forgets, the moon remembers. Somewhere beneath that silent grey dust may lie the first raindrop that ever fell on Earth, or the last relic of a civilization we no longer believe ever existed. Earth is not a museum. It is a restless, hungry machine, always moving, always remaking itself. The very forces that make it a cradle for life also make it the most efficient eraser in the solar system. Every mountain is ground down. Every ocean floor is reborn. Every monument, no matter how vast, is destined to vanish. The moon remembers because nothing ever touches it. Mars remembers because it is dead. But Earth forgets on purpose. Beneath the waves, the crust itself is temporary. The ocean floors we sail over today will be gone in less than 200 million years, dragged back into the planet's mantle like scraps into a furnace. Even continents are not safe. Their edges crumble into subduction zones. Their heartlands split and drift apart. No city, no wonder of stone, can survive the slow jaws of plate tectonics. Above the sea, the air and water join the work. Rain falls, rivers cut valleys, glaciers grind mountains into dust, deserts scour anything left standing. In mere centuries, a city becomes a ruin. In a few thousand years, the ruin becomes a hill. In a million, it is simply rock again, indistinguishable from nature's own. And then there is fire. Volcanoes pour over landscapes, sealing them under rivers of lava before grinding them into new minerals. Earthquakes snap and fold the land like paper. Deep underground, heat and pressure transform stone into something unrecognizable. Marble from limestone, schist from clay, civilization into oblivion. Even life itself conspires in the cleanup, with roots splitting walls, bacteria digesting metals, and fungi reducing wood to soil. Time is the final weapon. A few centuries test our architecture. A few million years annihilate our identity. 100 million years, even our most indestructible materials, steel, glass, plastic, dissolve into molecules, then atoms, then the background dust of the world. If humanity were to vanish today, what would remain? Perhaps a chemical signature in the rocks, a spike of carbon, traces of rare metals, microscopic beads of plastic. Maybe a strange layer mixing fossilized bones with bits of concrete and glass. But no buildings, no books, no maps, no memory. We would be reduced to an anomaly in the strata, a faint, nameless line. This is why the absence of evidence is not evidence of absence. It is not that ancient civilizations could not have existed. It is that Earth does not allow them to survive. The planet itself is the great filter, the silent undertaker. It needs no war, no asteroid, no conspiracy, only time. On Earth, history does not fade because no one writes it down. It fades because there is nothing left to write it with.